Hi everyone. So as you know, we are going through graphs. Okay. I'm so sorry for the writing. Yeah. So as you know that we are going through graphs in few days, and I'm not able to be consistent at all. So it's been a while. I have uploaded the video about graphs. Okay. So till now, what I have explained is BFS, that is breadth first search, and DFS. Okay, DFS traversal. Okay, so I've explained you the working of BFS and DFS. Okay, the code, whichever code you feel, I have given the code for them, and there are plenty of resource to study BFS and DFS. Okay, you might feel that BFS is quite easy than DFS. Okay, so wherever you find a better solution of DFS which suits you, okay, you can follow that solution itself. Okay, be a DFS code. Okay, right. So today what I am going to talk or explain is topological sorting. Okay, so what is topological sorting? Okay, there are few things that I'll talk in this video that no one would have told you about topological sorting, and your whole view about topological sorting will change. Okay, so the main agenda for this topological sorting comes from this thing that why we require topological sorting. Okay, and why is it told that only DAGs are allowed for topological sorting, right? And why not only AGs, okay, acyclic graphs? Why only directed acyclic graph? Okay, or why not only directed graphs? Huh? Why not only acyclic graphs? Let's say, let us let's say 0, 1, 2, 3, 4. This is a directed graph, right? But this has a cycle in it. Why won't we use this? Why can't we apply topological sorting here? Why? And let's say this one is an acyclic graph. Here also, where cannot we apply topological sorting? Why can't we apply in both the cases? Why only we require a directed acyclic graph? Why? Sorry. Only here we can apply our topological sorting. So this thing, the basic things, okay, this you all have studied what is topological sorting. It has an ordering. Okay, U to V ordering is to be maintained. What is that U to V ordering? Why is it required? Okay, so this pattern talks about, see, the main point here we need to talk is, in topological sorting, it is actually what it does, it sorts to organize a collection of items. Okay, or let's say items, or we can say task based on based on their dependencies. Based on their dependencies. What does it mean? let us take an example. Okay, let us take an example. There are a list of tasks to be completed. Okay, list of tasks. Okay, to complete. But to complete those tasks, there are some dependencies. That means, let's say task A can only be completed after the task B is completed, and after completing task A, task C should be completed. So we can say task A, for completing task A, it has a dependency on task B. That means if B is not completed, we cannot complete task A. So A has a dependency from B, and C will not be completed before A is not completed. So C has a dependency on task A. So see, here comes a graph, that is directory graph. What does this direction shows? That A has a dependency on its parent node, right? And the nodes are either items or tasks, right? I hope this is understandable and that this is understandable, right? Okay, let us clear this. No. So that is the reason why topological for this topological sorting pattern, we need to find a valid ordering of elements, right? We require a valid ordering of elements to after sorting. The main purpose of to sort is to find a valid ordering of elements, right? In the real world problems, to find a valid ordering for, let's say, the task. Okay, we can have a scheduling. Okay, scheduling of let's say timetable scheduling or algorithm. For in that case, we need a valid ordering of tasks. Okay, so for there we can make use of topological sorting, right? And that is the reason, if there exists, let's say, if there exists a cycle in a graph, or or cycle, or let's say the graph is acyclic but not directed. So if it is not directed, we cannot have a proper ordering of elements, let's say A, C, B. Okay, but there is no proper ordering. Is C has a dependency on A, or A has a dependency on C, or B has dependency on A or A on B? So that is unclear, right? So for that reason, we need a proper ordering. For that ordering, we need a direction that A is dependent from by C and B. If B is completed and C is completed, then only A should be done, right? So for that reason, there is the requirement of this direction, this direction, okay? And there is no requirement of a cycle, right? Why? If, let's say, if there is a graph A, B, C has a dependency on A from A, and then B has a dependency on C. So there appears an ambiguity. Let's say B is the starting task, okay, and after completing B, A should be completed, okay, and after completing A, only C should be completed, okay. But here we can see after C is completed, then only we can do B. But we know before, but for completing C, we need A to be completed, and A cannot be completed if B is not completed. Okay, it looks uh, quite complicated, but it is a simple one only. Okay, let's say B is done, then A is done, and then C is done. Okay, but B has a dependency on C, so B cannot be done. Since B cannot be done, so A can also not be done, and since A is not done, then C is also not done. So eventually we are having null. Okay, this is a void condition, right? a very complicated thing. That is the reason why there is no cycle to solve. There is no requirement of cycling to solve anything using topological sorting. Okay, so if in a question comes that there is a cycle, then by seeing this only we can say that it is topological sorting cannot be applied. And if there is a undirected graph, undirection, then also topological sorting cannot be applied. Okay, understood. Okay, so the keywords we can say is dependency relation. Second thing is task, or let's say jobs, or we can say courses, or elements, etc. Okay, these are the main ones, and many more things can be there. Okay, right. So the overall, the main concept of what is topological sorting, why it is required, what are the dependency, what task, okay, what are the ordering, valid ordering, okay, why cyclic is not required and why only DAGs are required. So that is the main concept behind any topological sorting question, right? What is dynamic dependency? If there is a cycle, then there occurs a dynamic dependency. Okay, so these things are clear by now, right? Now let me clear it all the things. Now we will solve not by coding. Finally I'll come up with the code of topological sorting in the next video. In this video is going to be very short, 10 to 12 10 to 15 minutes. Okay, now let us say there are some tasks. Okay, tasks with their dependencies. Let's say this is a task array. C is dependent on A. Okay, that means C will only be completed after A is completed. B is completed on A. Okay, let's say after this D is dependent on C, right? And E is dependent on B, E is dependent on B, and E is also dependent on D. Okay, let's keep this only small and short. So how can we make this dependency graph? Let's say A is dependent on A now, sorry, C is dependent on A. So A should be completed before C, right? Correct, this one is done. Now B is dependent on A, that means we can also say that B is also dependent on A. This one is done. Now D is dependent on C, that means C should be completed before D. This one is also done. Now E is dependent on B, that means this thing, right? And we can here see E is dependent on D also, is this, right? So you can say that this is a direct and a cyclic graph, right? But how? See, cycle, you can see that there might come a cycle from here, but here the direction says here, so cycle is stopped here. Okay, so this is a valid ordering. Okay, this is not a dynamic ordering, this is a valid ordering, and topological sort can be applied here. So how can we do topological sorting here is, now look here properly how topological sorting is done. So the one which is having no independent vertices, sorry, no independent what we say, edges, which has no independent, this one is having one, this node is having two incoming nodes edges. This one is having one, this one is having one, this one is also having one, only this one is having null. That means it is free of any dependencies, so this one will be completed first. So we can say A should be done first. After that, what are the nodes or tasks that are dependent on A? So we will see the neighboring nodes of A, that is C and B, right? So we will say C and B, right? Now take out either C or either B. So I'll take out C. I'll take out C. What are the neighboring nodes, or what are the nodes or tasks dependent on C? That will be the neighboring nodes of C. That is only D. So we will say D. Okay, the C is one is done, A is done, B is left. So B is dependent. The task dependent on B is E. So after B, the neighboring node of B is E, right? We'll say this one. So B is also completed, and after that we have D. Okay, D is left. So for D, which node is dependent on which task? E is dependent, but E is already done, na? E is already done. So that is not required. So this one is the answer, right? I hope this thing is understandable to you all. If not, to check out, okay, this to go back 2 minutes ago, and please see how I solved this problem. Okay, and how can we solve this topological sorting? See, what I performed here was I took the element which has no incoming edges. What does that mean? It is having a degree equal to 0. Okay, A is having 0 degree, right? In maps we say the node with 0 incoming edges has a degree of 0, right? And this one, let's say degree of B is only 1, it is having only 1 incoming edge. For E we can say it has 2 incoming edges, so it has a degree of 2, right? Okay, so how can we solve this using BFS? When I was performing this topological sorting, uh, you might have come with a solution. Okay, a thought might have clicked in your mind that we can solve this using BFS, breadth first search. Okay, let me explain that also. I'll just explain in this video, and in the next video I will not explain, I will directly jump into the coding part. Okay, the solution part. Okay, so this video is going to be a little long, I guess. Okay, sorry for the previous statement where I told that this will be a short video. This will be a little long, 20 to 25 minutes, and in the next video I'll jump directly on the code. So before viewing that, please check this. Okay, so now what I was performing, I was checking the node with 0 incoming edges, that is A. Okay, so what I'll do here, let us take another similar kind of array but with, sorry, no, graph but with numbers. Right, so this is the array. So what I'll do, I will just start a for loop and follow from 0, and what I will do, I will check any dependency that it has. If any array, any node does not have it, it's not dependent on any other node, I'll take it as our parent node. Okay, it will be given in the question also, but let us start using that. So I got 0. Okay, so what I'll do, I'll perform BFS. Okay, and with BFS what we require is a visited array and a queue, right? And here what we'll have, a list which will store the valid ordering of topological sorting. So we'll say top topolist, right? So we will start from 0. We add 0 in our queue. Okay, initially everything will be 0. And we mark it as visited, right? Now we take out the 0, we add in our list, and we check the neighbors of 0, that are neighbors of 0 are 1, 1 and 2. So we add 1 and we add 2, mark it as visited 1 and 2, right? Now what we do, simply take out 1, add in our list, check for the neighbors of 1, that is 3, add in the queue, mark it as visited. Now take out the next element from queue, that is 2, add in the list, check for its neighbor, that is 4, mark it as visited. If it is not visited, mark it visited, and add 4 here. Now take out the next top element, that is 3, add in our queue, list, check for the neighbors of 3, that is 4, but it is visited, so leave it. Now take out the next element in the queue, that is 4, add 4 here, check for its neighbor. Okay, it does not have any outgoing edges, so it does not have any neighbors. Okay, it has a neighbor but from incoming edges, okay, not from outgoing edges. So simply add the list, and now our queue is empty, so we have got our answer. When the queue gets empty, we get our answer, right? What we did in the BFS also. Now you will see that it boils down to a very simple thing. Okay, if we understand what is actually topological sorting, is a linear valid ordering, not linear, it is a valid ordering of elements having dependency on each other, right? U to V, that might become confusing to you all, okay, but this thing is very clear. Okay, dependency that should be valid, okay, and no dynamic dependency. Dynamic dependency is not. What is dynamic dependency? That during the execution, let's see, it was 0 or 2 was dependent, 2 had a dependency from 0, but while executing it changed from 0 to 1, so that is not okay. It has a static dependency. Okay, now let us see if our answer is correct or not. Okay, this answer is correct or not. Now see, we had 0, so okay, it is correct. 0 has 1 and 2, so 0 will go 1 and the 2. Then 1 has 2, oh sorry, 1 has 3, 1 has 3, 2 has 4, and 3 also has 4. Okay, correct. 0, 1, 2, 3, 4. Or we can also say 1 has 2, 1 has 2, 1 has, sorry, 0 has 2 and 0 has 1. 0 has 2, 0 has 1. Now we can take 1 also. Okay, not 2. Without 2 we can say 1 is having 3. And then we can say 2 is having 4. So 2 is having 4. This one is also correct. Okay, and we can also say that 0 is having 1, 0 is having 2, then 2 is having 4, and then 1 is having 3. This one is also correct. 0 1 4 3, 0 1 2 3 4, and 0 2 1 3 4, and other can also be formed here. Okay, so there can be a very too many options for solving topological sorting. Okay, too many answers after solving topological sorting. Okay. So I hope this was uh, clear to you all. So we performed this using a BFS algorithm. Okay, using BFS. Okay, we can also solve using DFS, but before that, in the next video I'll give you the coding part, and then we will solve using the depth or such. Thanks for watching.